Hello students, today we will study diffraction and polarization of light. What is diffraction? It is a phenomenon of light or bending of light at the sharp edges of obstacle or spreading into aperture is called diffraction of light. Grimaldi, a name of the scientist, discovered the diffraction first of all for sound wave. You can simply say whenever there is a straight line transmission of light, diffraction is not there. If there is a deviation in straight line transmission of light, means diffraction is there. Okay. You can see if this is the source and this is the opaque obstacle. And if this is the screen. If there is a straight line transmission of light like this, if here in this case, if here at this place, if no light is there, only straight line transmission took place, means no diffraction. Okay. This is source of light. This is the case when no diffraction has taken place. Okay. Now let's see another case. If this is the circular aperture, this is a wall, and if this is the source of light, and in case if this is the screen, if light is there everywhere in between, if light is there everywhere in between, this straight line transmission is there, means no diffraction. If light is here somewhere, okay, then diffraction will take place. Okay. So let's see the condition of diffraction given by Grimaldi. If A equal to size of aperture or obstacle, and lambda equal to wavelength of light, means the condition for diffraction, if A upon lambda equal to 1, then this is the condition for best diffraction. If A upon lambda approximately equal to 1, then good diffraction. If A upon lambda very greater than 1, or if A upon lambda very less than 1, in this case no diffraction. No diffraction. Okay. Now dear students, we will be looking for Fraunhofer diffraction. Okay. in single slit experiment. This is Fraunhofer diffraction result for single slit experiment. This is the diagram for single slit. Here we place a convex lens, and this is the screen where we observe the diffraction fringes. At the center point, we obtain central maxima. These are plane wavefront. At the location of central maxima, the path difference and phase difference remains equal to 0. Okay. If let us assume this is the point where secondary wavelets are reaching here from this point, like this, and this is the path difference. Okay, A, B, and N. This Bn is the path difference. Okay, and this is the theta n or theta n dash. We will write here theta n for dark fringes and theta n dash for bright fringes. Okay, theta n will be the angular position of nth order minima from the direction of central maxima, and theta n dash will be the angular position of the nth order maxima, secondary maxima, with the central maxima. Okay, and in a very similar way, xn and xn dash we will be writing. Okay, dear student, if A is the slit width, and this distance is capital D, that is equal to F. Okay, now let's see the situations. Condition for nth order minima at screen. This is the path difference for minima. This is the equation here, A sin theta n equal to n lambda. Now dear student, for first minima, this is the position of first minima. This is also first minima, and this is central maxima. This central maxima is located between two first minima. Okay, let us assume this theta or theta 1. This is the angular position of first minima with the direction of central maxima. Okay, semi-angular width of central maxima. So we can write for first minima, this is the equation, A sin theta equal to lambda. So dear student, we are getting sin theta equal to lambda upon A, theta equal to sin inverse lambda upon A. What is this theta? This is semi-angular width of central maxima. Semi-angular width of central maxima. And dear student, what about the linear position? This is the linear position. Okay. When angle is small, tan theta is equal to sin theta. Tan theta equal to x1 upon d equal to x1 upon f. F is the focal length. Okay. So dear student, lambda upon a equal to x1 upon f. So what is x1? F lambda upon a. This is the linear position. This is the linear position of first minima from central maxima. Okay, and This is the semi-angular width of central maxima. So complete angular width of central maxima will be 2 theta. That is equal to 2 sin inverse lambda upon A. Okay. Now, dear student, let's see. For nth order secondary maxima, this is the equation of path difference A sin theta n dash equal to 2n plus 1 lambda by 2. What is theta n dash? This is the angular position of nth order secondary maxima from the direction of central maxima. For first secondary maxima, n equal to 1. So dear student, let's see. This theta 1 dash is the angular position of first secondary maxima with the direction of central maxima. So we will be writing A say sin theta 1 dash equal to theta 3 lambda by 2. So sin theta 1 dash equal to 3 lambda upon 2a. So theta 1 dash equal to sin inverse 3 lambda upon 2a. And if you want to know the linear position, this is linear position of first secondary maxima from central maxima. So we will be writing tan theta 1 dash equal to x1 dash upon d equal to x1 dash upon f equal to 3 lambda upon 2a. So x1 dash equal to 3 f lambda upon 2a. In that way we can solve other problems also. Let's see. If intensity of central maxima is I naught, then intensity of first secondary maxima will be I naught upon 22. This intensity can be calculated by this formula for secondary maxima, I equal to I naught sin alpha upon alpha whole square, where alpha is phase difference. 4 first secondary maxima, dear student, n equal to 1. So alpha is 3 pi by 2. So I equal to I naught sin 3 pi by 2 upon 3 pi by 2 whole square. This is equal to 4 upon 9 pi square I naught. This is approximately equal to I naught upon 22. In case of diffraction of light, diffraction fringes are of unequal width and unequal intensity. Okay. This is central maxima. This is first secondary maxima. This is second secondary maxima. Approximate. Dear student, diffraction fringes are of unequal width and unequal intensity. For interference, two coherent sources are required, but for diffraction, it is the result of infinite coherent sources. Okay. Now let's see about polarization of light. What is polarization? Dear student, restricting the vibration of electric field in a particular plane. Restricting the vibration of electric field in a particular plane, okay, is called polarization. This is very small chapter but very important chapter. Restricting the vibration of electric field in particular plane is called polarization. Now, dear student, let's see the diagram for unpolarized light. The dot indicates vibrations perpendicular to plane of paper, and the arrowhead indicates the vibration in the plane of the paper. This is the diagram for unpolarized light. And this is the diagram for perfect polarized light where vibrations are perpendicular to plane of paper. And this is the diagram for partial polarized. This is the diagram for partial polarized light. Okay. Now, here very simple fundas are there. Three important points are there that to be noted. First point. Whenever in any question it is given, whenever any unpolarized light passes through polarized, then its intensity becomes 50%. Okay. This is the first general statement. Whenever any unpolarized light passes through polarizer, its intensity becomes 50%. Okay. If this is the polarizer, then if this is incident light, its intensity will become I naught upon 2. Okay. This is the first statement. Now listen, Malus law. This is applicable for polarized light. When polarized light passes through polarizer or analyzer, this is intensity of transmitted light, this is intensity of incident polarized light into cos square theta, and theta is the angle between transmission axis of polarizer and analyzer. Okay, theta is the angle between transmission axis of polarizer and analyzer. Now, see, this figure is known as cross polarized. Because theta is 90 degree. So if this is I1, this is I2, I2 will become equal to 0. This is parallel polarized. When theta is 0 degree, This is cross polarized. This is parallel polarized. This is I2, this is I1, and this is I2 equal to I1, because here theta is 0 degree. So this is the graph. If this is I, this will also become I. Okay, this is the graph. Now let's see one important relation, that is Brewster law. When unpolarized light is incident on a transparent slab, this is unpolarized light. Incident on a transparent slab at particular angle, that is theta p, that is Brewster angle or polarizing angle, then reflected light becomes perfect polarized. This is reflected light. It becomes perfect polarized, and reflected light becomes partial polarized. This is partial polarized. This angle is 90 degree. So this angle is 90 minus theta p. Apply Snell's law. If refractive index here is mu, then 1 into sin theta p equal to mu into cos theta p. So dear student, this tan theta p is the Brewster angle or polarizing angle, that is equal to mu. So theta p equal to tan inverse mu. This reflected light becomes perfect polarized only in a situation, okay? This reflected light becomes perfect polarized only in a situation when angle of incidence is polarizing angle, okay? So dear student, this was all about the diffraction and polarization. Now in the next lecture we will be looking for the problems, okay? Thank you.